Okay, hi everyone. We'll get started. So before I give it over to our amazing speaker today, just a couple of housekeeping items. This meeting is, or this webinar rather, is recorded. So we'll share that on YouTube once it's ready with all of you. So don't be afraid if you have to leave early or things like that. We'll have it online for you. For questions, we ask that you hold them until the end. We should have some time for Q&A. If for some reason we don't get to your questions, feel free to join our public Discord and you can ask questions there and we'll pass them along to Jon to get some answers for you or to the team. So I'll post that link in just a minute. Let me see, right there. Posted it in there. All right. Well, thank you everybody for joining. Thank you if you're watching us live. We really appreciate you taking the time to join us. Also, thank you if you're watching the recording in case you couldn't make it live. And with that, Jon, I'm going to give it right over to you.
Okay, hi, I'm Jon Strabala, and I'm the principal product manager for eventing and search. And search encompasses our new vector search offering at Couchbase. So essentially, I hope we can all see my screen now. I sometimes
Yes.
share the wrong screen. So hopefully we see AI creates an opportunity for new application design.
Yes, we do.
Okay, fantastic. So basically, what we're really trying to do with vector search is to give you tools that you can make a new set of hyper-personalized applications and also ease your development in the generative AI space. And the way we really do this is essentially we store vectors and we search vectors. And so I'm going to spend a little bit of time talking about this. A vector can be made out of a chunk of text, or it could be made out of a single word, or a vector could be made out of an image, or any sort of media fragment, audio or video. And the way vectors are made, they're made out of embedding models. Okay, an embedding model can be very simple, or it can be very complex. And that translates, our object over there on the left into a multi-dimensional vector. Image vectors might be smaller, they might be 256 or 512K dimensions. A text vector, like if we're talking about OpenAI, typically it's 1536, but they're up above 3K now, and they can go up to 4K from embedding models from Cohere. Our initial version of Couchbase limited the vectors to 2K or 2048. And when we have our next point release, which will be 762, we will be supporting 4K or 4096. So essentially in Couchbase, we store our vectors with the document. So over here, we see the bright orange where we just say, hey, this description vector is just stored in the document. And through DCP, which is our technique that we move data within our microservices, the search service receives all the mutations, whether it's an insert, upsert, or even a delete, and it will maintain that vector index in real time. So essentially, there are a lot of embedding models out there. Personally, I like to play with OpenAI's just because I'm used to it and I've been doing it for months. But if you go to Hugging Face, you could see hundreds of embedding models, and there's leaderboards and whatnot. So our typical application would be, you have an embedding model and an application. The application basically sends a vector, which is its question, what it's trying to match. Now, that question could be a textual question, or it could be a vector of a portion of an image, and then we'd get back a response. So when I say I typically use OpenAI, it's not hard to generate a vector. There's a couple lines of code is all it takes, but you do have to have, an account and an OpenAI key, a bearer key in order to do that. So typically what we have when we're dealing with just a vector search engine, before we add all the layers and goodness on it, is we will have your application, and maybe you'll do a bulk load, or maybe you'll load things one at a time. the JSON document with the vector could be loaded into the Couchbase data service, and quickly the search service will respond to that mutation and maintain a vector index. So that develops your data corpus. It could be as small as 5K or even 200 items. It could be as large as 25 million or 50 million or 100 million items. But once your corpus is in there, now it's time for your search logic in your application. And essentially what you would do is you would get the embedding using the same embedding model, and you would generate a vector, and then you would ask the search service, hey, return me things related to this vector. And typically we do like the top 3 or top 5 or top 10 results. And that's essentially how everything works. So what I'm going to do is I'm going to talk about our basic architectures. You just saw that. This is a little bit more detail. The orange is how we get the vectors into our vector data store, and the purple or pink is how things are queried. Now, this is the basic semantic or similarity search application. In Couchbase, since we have this service called an eventing service, we could actually use the eventing service to maintain your vectors. We could use it to create the vectors from scratch, or we could use it to update vectors as portions of your document, your JSON document, change to make sure that you're always consistent and up to date. Essentially, it's the same architecture. Then we go into what we would call your traditional retrieval augmented generation. Okay. And this is how we would take something like ChatGPT and enhance it with your own company specific secret sauce, like it'd be your own corpus of, let's say, how you do things, whether it's programming, whether it's developing business plans, et cetera, et cetera. And this would actually help prevent hallucinations. I mean, if you just go to ChatGPT and say, how do I write my business plan for company X, that's my company, to do an RFP for company Y. Now, obviously something will come back. It might give you totally nonsense. But if you actually use a RAG model, that question would go in to your own data corpus, which stores all sorts of stuff, and you'll get your top N hits that actually then is the relevant knowledge with the original question would go to an LLM and get formatted, and you get much better, much more focused answers. And we'll be doing a demo on that to show how that all works. Now, here's an architecture for a recommendation engine. We might have a user embedding that comes back at login time. And that user embedding might be the age, the gender, color preferences, fashion preferences, whether they, want to be a, construction worker and they want to buy clothes that last forever, or whether they're into high fashion. And these things, based upon the context of maybe where they are in a website, might give you a ranked category of items that they would possibly be interested to buy. And this keeps the users more engaged and increases sales. And the last reference architecture would be a media search application. And one thing to note about Couchbase, we only store 20 megabytes per document. Therefore, you're not going to want to stick in a video into Couchbase. You would probably stick in a reference. So in this architecture, we can think of these images over here as merely a path to a web server or content distribution network, okay? So these might be the images that you serve in a web server. And so the image and the vector might be more akin to be a reference to where the image is and the vector. And then we'll get back references that we could look up for the user. So what I'm going to do now is I'm going to go into a very basic three-dimensional vector that we can all visualize. I like to use the RGB model, which is web colors. Sure, we can encode 16 million colors with 3 numbers, 0 through 255. And so what we're going to do is we're going to say, we're going to load a data corpus, and we're going to have this fictitious embedding model. It's just called RGB. So say I stick in a word and then I get back a vector, okay? And that's all an embedding service does. Now I have kind of a bluish one and two orangish ones. And then when I do a search for something like peach, I would hope that I get things that are close to peach. Now, I have in the demo we're about to run, I have 153 colors, okay? And as you can see, peach, apricot, and cantaloupe are very close to each other. So let's just walk a little bit further here. And when I get done with that small demonstration using Couchbase, we'll go into a much larger demonstration where we have higher dimensionalities using OpenAI vectors, showing you how that works. So the demo data set will always look something like this: brightness to the human eye, the name of the color, a Euclidean distance vector, which is what web colors are. I am also doing a normalized vector, which is a dot product. It has the formula that we do to normalize a vector. And then the ID would be the hex color code, which will be absolutely related to the decimal codes here. I put in some other stuff, the wheel position, primary, secondary, tertiary, and then I put in some verbs, the deep, rich, sophisticated, that are related to this particular color. Then I might have a very long description. I'm not showing it here. And I will make an embedding vector out of that description with OpenAI via this embedding model. Okay. So that's our data set that we're going to take a peek at. And I put in some sections of this color. So, we're going to do a search for peach first, and then I might use a different, I might use the dot product version, because that doesn't search for colors, it searches for shades of a particular color. So it's important to understand what your similarity metric is, because it can really impact what comes back. So in Couchbase, I've got some data already loaded up, okay, and I'm going to search for peach. This is not the SDK, but this is just the way we search in the search service. So I'm going to paste in this particular search, and then we're going to talk about it, okay? Now, it did come back with peach, and it did come back with apricot, and it did come back with cantaloupe. And I'm hoping that, peach, apricot, and cantaloupe are really close by. Now, we did not write this to do colors, and you might say, hey, Jon, what in the world? I mean, you are actually searching for peach exactly. So I don't have to search for peach exactly. I could change that to 59. I could change this to 141, and I could probably even make an illegal color 256. It's just a vector. I search this and we will get back peach and apricot and cantaloupe again, because they are the closest colors in vector space. And when I'm talking about vector space, and I would be a little bit, I want to say one thing here. When you do full text search, if you search for words like big cat, you might get back like cat in a hat or big hat. There's no semantic meaning. But when we do it in vector space, when I search for big cat, I could get back tiger, leopard, lion, puma, jaguar. And that is the beauty of vector when we're searching for vector. Now, we just did a very quick query on what we said was peach. Now I don't have to cut and paste these things. Once I get this templated query, I can just say, hey, you know what? I'm going to search for black. I happen to know black is the absence of all colors, right? So I'm going to get close to black and I'll try to search for that. And sure enough, we get black. Now let's look at what this is. I showed you the schema of the data, but this is the data that's actually black, okay? Zeros. Now this is kind of interesting. Black, when it's a normalized vector, will come back with the same value, 0.577. Now, that's kind of interesting. I'm going to change this vector to dot, the other vector that's in there, and we'll query it again. Now we're going to get all shades. And here I did 001, that happens to be blue or navy, okay? So when I look at this, if I have zeros here, this always normalizes to 1 here. So this is pulling in shades of blues, okay? Because it's a different similarity metric. And so it's important to understand that usually small dimension vectors like 3, sometimes like 16 or 128 might be a Euclidean distance. Almost invariably, you will be dealing with normalized vectors, whether it's cosine distance or normalized vectors. OpenAI happens to be cosine distance that's normalized, so it's a dot product. When you get into high dimensional space, the curse of dimensionality makes everything appear to be the same distance in Euclidean space, so you will be doing like a dot product vector. So I actually just did the shade search. Now, one thing that bears taking a look at is we can do hybrid searches in Couchbase. And hybrid is very interesting because right here I'm saying, look, I want to do a traditional full text search side query, and I want to find a brightness between 70 and 80, okay? And I'm going to, get back some things. And then I also want to like search for red, green, blue. So I want to search for purples because I am using the normalized vector, which brings back shades of a color. And I'm going to do this query and it's going to be scored. And if I get the same ID from both traditional full text search side and the vector side, then it'll be boosted in the score. So I'm going to go ahead and we're going to just, kind of hide that expanding and we're going to run this. And as you can see, we got between 70 and 80, and we got a color that was purple. Okay, between 70 and 80, a color that was purple again. Now we got a color that was purple, but we weren't between 70 and 80. And the reason why is that the vectors are being ORed together. Okay. And that's kind of an important concept. When we are doing our vectors, match none, that says turn off the traditional side. And over here, we're doing one or more vectors because it is an array of vector search objects. I don't want to change that. But when these things come back together, this is another form of hybrid search, and we'll be demoing that together when we mix it in with SQL++. But the important thing to know is that these two sides are ORed together. But if I'm using our SQL++, you can actually and things to like really winnow down your space. So when this comes back, we actually have a lot of goodness in Couchbase where we take a very robust library known as FICE from Facebook for similarity searches. And then we've like added Couchbase goodness to partition it into multiple partitions or shards and also across multiple nodes. And this is completely hidden from the user. You just say, hey, how many partitions you want? And then we take care of all sorts of the underlying logic on how many centroids are going to be and how many probes we're going to make, and things will just work. And now we're going to bounce back to that demo that I'm talking about. We just kind of walk through this. We walk through a hybrid search, but not in SQL. And now let's talk about higher dimensional space in Couchbase, okay? So a higher dimensional space might be something like I have travel sample inventory landmark here, and I'm going to go in here and we're going to actually take a vector here, okay? And when we work with vectors that are very large, they're kind of painful. This isn't legal because I don't have a legal array. I go dot, dot, so many items removed. Now I've got to match the dimension of my vector. Okay, this is a dimension 1, and it's not going to match the space. So I happen to know that I want something. This is like 6 lines of code. We'll make a vector. This is like a little web tool I wrote. It's 55 lines of code. So all I'm going to just do is say, hey, good spicy food in Europe with good sized portions. I'll make the embedding. I'll copy this embedding right here, and we'll go in and we'll, paint. And I say, this is painful. This is just our UI. And I will highlight this vector and replace it. And it's legal. So I run it. And obviously I did something wrong. I don't like doing that. Let's try this again. And I'll just sort of run it this way so that I don't get a syntax error. Okay. These are little tools that were helper tools. So I just basically did a thing on what is fun to do in Paris. Okay. And we can do anything we really want. And I could change this to Britain. And we'll regenerate a vector there. It's not rocket science. This is like a mini application. And now we're getting what's good to do in Britain. Okay, and all we're doing is we're matching this similar vector, okay, and trying to get something. And now this gets really fun. And I'm going to jump into something about how things get fun. So I have something that is a question, much like this, okay? And this is almost perfectly the same on what's in our database. So I'm going to search it. So I say, hey, what's the only medieval fortified bridge? Okay, so if you look at this, I'm saying, I didn't use bridge, I used water crossing. Okay, now we can keep doing things crazy and really, really get far afield from what that item is. I'm going to update that and then we'll query it. And we get the same answer. But if you look at it, I'm doing a water crossing. I'm doing United Kingdom. I'm not doing Britain. I'm not doing a gate tower. I'm doing a checkpoint and not the word middle midspan. And we can even misspell things, okay? Rather than kingdom, so the misspelling is intentional. We'll do that query again. And as you can see, we keep getting the right answer because this is similarity in semantic search. And I'm just showing that how that works in Couchbase. And we could do the same thing for lower dimensional vectors. And also we can do the same thing in both our self-managed product and our cloud product. So if I go into search, I have that same color data set loaded. Okay, so here's my search index that we have. Why don't I just make an index from scratch? Okay, so I'm going to go back to search, and then I'm going to make an index from scratch to show you how easy this is. So I'm going to go in here and I'm going to go, okay, I'm going to just make an index and we'll call this test. All right, so all you have to do is select your primary bucket, travel sample, inventory, and I'm going to do something with landmark because landmark actually has a vector. I'm going to store the name. If I can find the name, it's there. We're going to store it, and I want that to come back in my search results. And I have something called description somewhere or content. We'll find that in a second. So here's content, and we will also include that in our search results, and I'll add it. And the last thing I want is I want this embedding vector. I need an embedding vector because I'm going to be doing vector search. And I believe I forgot to put the embedding vector in here. Okay. Let me just switch to something else. This and color RGB. So essentially what I can do is I can put that embedding vector in and it intuits the size. This is going to be dot product. I have to make sure I know the right similarity metric, and it is dot product. And I'm going to optimize it for recall, and I just add that. Okay. And I'm going to put the color in, and we're going to include the search results. That's it. That's all we had to do. We're going to create this index, and up we get it, and then we have this index. Now we can search the index, and over here, I'll go back to say our let's look for this guy first, where I have to get to the right. There we go. So we can search this, and I'm searching. I should be searching for a purple. And of course, something didn't happen right, and I don't know why. Sometimes demos don't work out right for me. That should have definitely worked, I think. I don't know why. So vector color, and I called it test. And let me go back to the list, and it should have worked. Let's see if this search works on the existing index. Yes, it did. So I'd have to like go in. I must have made a mistake. Unfortunately, I don't know what mistake I made. So I'm not going to go back to that. So we go back to our search, and I was trying to say, hey, it's easy to make a vector index. Let's just take a quick peek at this. This should have been trivial. I'm in here. We have color that's stored. Oh, I didn't put in that vector. Okay, so I was searching the wrong vector. There's always a reason. Okay, so we're going to update that index, and then we're just going to go one more search and finish this up. So I paste that in there, and this will obviously work at this point. Okay, we were only putting in the color on this, so it's not hard to make a vector index. Okay, and that was the key thing there. What I'm going to do to sort of finish up this, we are going to have a little bit of fun. We were like looking up this monogradient bridge. So I'm going to say, hey, what is fun to do in Paris? Okay, that smells. Okay, so I'm gonna search for something like that, and then we're gonna update that vector, and we'll search. And let's see. Oh, it's like some sort of sewer tour. Okay, well, you can go full circle and just do an LLM, and I just go, hey, I asked what is fun to do in Paris that smells. We got 3 facts back. We give it a prompt, and we send it to an LLM, and then the LLM gives us a nice formatted answer. And so that's kind of beautiful. It seems that we're interested in off the beaten paths, and so we get this neat thing back. So this is reg that I'm just showing you. It's not hard to do. I've just kind of had this little micro application plugged into the UI with this experimental set of tools here. So now we're going to show one of the great powers of Couchbase and vector search, and this is actually what we're going to do is we're going to do a hybrid search where we combine a vector and SQL++. So I'm just gonna copy this if I can actually get my I can't. Sometimes I just can't win because I can't. There we go. All right. So I'm going to go back into a the SQL query. Okay, I actually have an embedding that would work, but we're going to do this from scratch. So we start off with this. Now I need an embedding, okay, because this isn't a real vector. So what I want, great spicy food in Europe with good sized portions. Now I'm going to go here and, I'm going to just go ahead and make a big vector. And let's make sure I make it, paste that in. And I'll copy this vector, copy, and we'll go back here and we'll just paste this in here. Okay. And now before I run this, I want to show you that there's something really weird about what I asked it to do. I'm forcing the activity to be eat. I'm forcing the country to be UK, but I am asking, hey, what's great food, spicy in Europe with good sized portions? So what's going to happen here? I'm going to execute this query, and let's see, what did I do wrong here? I made an error. Let's go back one and just see. We execute this, and no data to chart. What is this doing to me? And oh, okay. So now, okay. So let me go back here and grab this. I must have go down one and then over. Oh, yeah, that's what's happening to me. Okay. I'll go here. Oops. my selection is just so paste that in there, put a comma in, and execute it, and it should work. There we go. So we force the country to be United Kingdom, okay? And then we get good quality, predominantly French food, beautiful food, wonderful stuff. It's trying to do the best it can through the boosting and the oring of things together. And so I'm forcing it to be United Kingdom, and it's trying to get things that are close to Europe or things that might be European. And so that is kind of working. And, when I don't have my syntax errors. Now, we're all interested in making applications, okay? So let's talk about applications. This is a complete application in Langchain. Langchain is a framework that allows you to do chained natural language processing, AI stuff very easy. And one of the nice things about Langchain, I mean, I just import our first class things so that we can use the Couchbase SDK. Then we import the Couchbase community, which is the Couchbase Vector Store. And I can set up OpenAI embeddings. I can, that's that import. Now, so all I'm doing here is I'm saying, hey, I want to talk to Capella, okay, which is our cloud thing. And I want my embeddings to come from OpenAI. And now I open up a vector store. So you could find a nice example that might use Pinecone, but you decide you want to use Couchbase, and you can just swap this out. And this particular example is going to only load words. It's going to vectorize these words. There's 10 words, and it's going to make 3 one-word queries. So we're going to actually do that right now. And so let me find this. So here we go. We're going to actually do that. I'm going to activate a virtual environment. You can set up a virtual environment just like this. And so I've activated it, and I have a couple things here. I have a GitHub repository, and there'll be a link on the next slide when we go back to the demo. So this is a GitHub repository, and it has some items in here, okay? So if I cat this template setup, I have to set up some environment variables. It's the Couchbase login, and then it's where we want to put our data, and then our index name and our open API key. Now, I don't want you guys to know my open API key. I already copied this template over and filled in the blanks. So I just sourced that. Now I can check to see, hey, am I able to talk to OpenAI? And if I do, it says, hey, it's cool. I could just make a vector right there. But we don't really like to cut and paste vectors. We like to use applications, okay? So let's check our connectivity to Couchbase. So this verified I could talk to Couchbase. And it also says that, hey, I'm running a version that's greater than 7.6 or equal to that. So I'm good to go. So this program, if I cat it, just so that you can see what it is, this is the exact same program we had, okay? And then, for query and Vespa, Puma, Nugget, okay? So all we're going to do is we can run this program, but when you first download from GitHub, there are some things that we do, and I'll show you that when we go into the next one. Let's just run this and see that this happens. Then we'll run a more complex application. But this is just the basic stuff. So we've added those items, and as you can see, it returned motorcycle twice. Well, because I already ran this, so let's just clean it out, okay? And I say, okay, well, let's clean that out. And so now we have 10 items only. When we run it a second time, it'll load it from scratch, and we'll talk about what happened. Okay, I searched for Vespa, and it returned motorcycle, bicycle, car. I searched for Puma. It returns tigers, lions, and bears. And that actually makes a lot of sense. I search for Nugget, and I get slab, stone, rock. Now, I might think Nugget is closer to a rock, but this shows you how this semantic similarity search works on really simple words. Now, we could just go in and we could edit this, and we could just change something slightly. Let's see, where is that program that we're running? It's right here. So we're going to run into this, and we're going to do instead of Puma, let's add another query and let's just do links. Okay. And we'll just run that again. Okay. Now I didn't run the setup.pl. Okay. But when I ran links, it says lions are very close to links. Okay. If I ran the setup.pl, I would have started kind of fresh. So just wanted to show you that this was live, and we can do the exact same thing in Capella. I was running on a local server. This is going to run on Capella, and I think I've already got the environment set up. Yep. So setup.py, and that's going to run, and it's going to say, hey, do you want to flush things? Now, when we do Capella through the SDKs, I did have to create the bucket in Capella. So when I'm saying I had to create the bucket in Capella, we're running around here. I had to actually create that vector demos bucket in Capella. So if we go in and we look at this in Langchain, we have 2 collections in here, and I'm doing my basic stuff. There's 10 documents. And so we can actually run this, and this will make sure that it's all flushed. Okay. So there shouldn't be any documents that I can find. I go in here looking for documents, and I just want to prove that it's empty. And so vector sample, this is in vector demos. This shouldn't be Langchain, and this is basic. So get documents. We don't see anything. That's good. So now we're going to run our program, and it will load the 10 documents, and and we're doing this across the net to the cloud, and it does the same thing. I'm just showing it's nice, it works. And now let's get our documents, and we see that, hey, we have our documents. So that was kind of the basic application, and then we have one more application to show you, and that's the much more advanced application, which is the WebReg application. So I've got these 2 items here. So if I open these things up, they have complete directions that you go, okay, this is what we want to do. Set up your environment. You can activate and deactivate your environment, install your requirements, set up your code, and sort of test some things out, and then run it. Okay. And if you don't want to do that, there's a video that'll show you exactly what I was up to. Okay. So now what I'm going to do is I'm going to take one of these demos that I was playing with. Okay. And we're going to go up one, and we're going to go into this particular demo. And what this is going to do is we're going to be chatting with PDFs. Okay. And so I'll just do the same sort of thing that we did before. We'll set up the environment variable, which will be a whole bunch of things like this. Very similar, except it also has a web login password. Okay. So we're ready to go. And this particular demo actually requires me to run this web runner called Streamlit. So grep stream from star.md, which is from the GitHub repository. And we get in here, and let's see, I was trying to, this is the command that it takes to run. So I'm going to run this, and it's going to fire it up. Okay. So now I have this local address space that we're going to go to, and it should be right here. Paste that in there, and it brings up an application. All right. And I have a little web protection for what it's worth, and we're ready to go. So what we're going to chat with our own PDFs. Okay. And we're going to show the power of RAG. Now, I happen to have a few PDFs that I will play with here today. And one of them is this guy. Okay. And that's veritas.pdf. It's a glamping retreat that my daughter is opening. Okay. So what I just did is I vectorized this PDF into 30 documents. Okay. And what is in this PDF? It's a glamping retreat, as I said. We're got a whole bunch of pages, and it talks about what they do, and the cost, and what they horseback riding, and it's fairly extensive. So we've got that in there. Now we can actually ask some questions of our own PDFs and show you exactly how RAG is working, okay? And let's see, I want to find what I want to ask, and because I kind of canned this. Okay, there we go. That's what I want. Let me just copy that. It's easier for me. Okay. So I'm asking it a question. What this will do is this will go to Couchbase and it'll get some information from those vectorized chunks of stuff, and it'll take the top three. It'll send that with the question, and then boom, we get this great answer back. Now, when we go directly to ChatGPT, it doesn't even know what this project is. Okay. Now we can have a little bit more fun. I'm going to pull in a joint venture between Ford Motor Company and ADT on security for trucks. Okay. So now I've got this business plan, and we'll just take a look at the business plan right now. Let me open that up and let's take a look at what I loaded. It's a business plan, and it's got an executive summary. It talks about the market share, the viability, and all sorts of stuff, and how much things cost, and what the ability is to do things. So I'm going to close all tabs. I don't need any of that open, and we will get rid of that. And we're going to ask a question about this. What's the total addressable market share of Canopy? So you could imagine that you have all sorts of business plans. Let's say you're doing RFPs and RFQs, and now you can like pull out like your internal knowledge. Now, this is actually right. I mean, 7 million vehicles in Europe, 24.7 vehicles. Okay. Now, it doesn't know. ChatGPT doesn't know. It probably thinks it grows cannabis. So, that's the beauty and the power of RAG. And we can have even more stuff we can do. We've got these two pieces of data in here, okay? And now I'm going to go, how can Veritas Island utilize the core expertise of Canopy to enhance its operations? Now, remember, Canopy secures trucks and prevents theft, okay? So we're just kind of like asking this question, and then we're seeding the GPT, the LLM, and without that seeding, you don't really get an answer. So that is pretty much some of the core stuff that I wanted to show you. Now, I do want to point out from a performance standpoint, we can actually, I'm going to do a little bit of run here, and I'll talk about what I'm doing. Okay. So I am running against 50,000 vectors. Okay. Now I only got 20 requests per second when I was warming up. That was a one query. But once I'm warmed up and we start to get caching, we're almost at 500 requests per second. Now we go to a 500,000 corpus. Okay. And once we're warmed up, we're at about 140 recs per second. And this is a single node. And now I go to 1 million vectors. And as you can see, we've slowed down almost by a factor of 2, even though we've increased by a factor of 10. And one of the things I do want people to understand is vector search is hard. I mean, when we're doing, let's say, prefix searches and search, we can hit like 20, 30,000 requests a second on this same piece of hardware. And the piece of hardware is, I have 24 VCUs, 12 physical cores, and they're running at 2 gigahertz. Okay. So I do want you to be aware that you do need a box that has enough power. There are situations, I mean, Couchbase does have a competitor, okay? It's MongoDB. If you underpower your box, this is Mongo, okay? Now, these are really low-end boxes. These people, they only have 100K docs, and they're complaining, well, it's taking 4 seconds, okay? Well, they're swapping, okay? So, an M10 is really, really underpowered for vector. So I just wanted to point out that yes, you do need a box. I mean, and when I'm saying a box, you want, probably at least 8 vCPUs and at least 16 gig of memory, because once you fall out of the memory envelope, you will run a lot slower. So this is essentially what we wanted to show. And I do want to say one thing. The 760 release is when we went GA with Vector. And when we went GA with Vector, so I'm gonna just use this thing. There's a million vectors here. I'm searching it with 8 clients, okay? And I just did the search for 10 seconds, and we're getting 75 recs per second. We are at least 10 times faster in 762, okay? So early days when we did 760, it's great for prototyping. We recommend people, if you have lots and lots of vector, just wait till June when we have 762 out. And I will take a look to see if there's any pressing questions in the chat, and there isn't, so I'll open it up. If Caroline could, direct that, or make sure that you guys can open up your mics.
Yeah, absolutely. If you want to talk, you can raise your hand or put it in chat, put it in the QA, and we'll get to it. If there is no questions right now, if you have questions after we wrap up today, feel free to join our Discord. I put the link in chat. You can join there and ask any questions, because sometimes I know it's as you're processing things, you might not have a question right now, but then as you think about it, you might have a question later. But Jon, thank you so much for taking the time to talk to us today. Very much appreciated.
No, that's what I'm here for, and I enjoy it.
Well, I appreciate it. It doesn't. Oh, there's one. Paul, would you have any suggestions for dimensionality reduction for models that output bigger vectors?
Okay, so anytime you do dimension shrinkage, okay, and when you use NumPy, it's quite easy to do. Your accuracy and your recall will drop. There are 2 metrics that tell you how good your vector system are. Accuracy is whether or not you got the top hit. Okay, so if I'm testing my system, I want accuracy in the 95% or above, or maybe 99% or above. Recall, it says if I get 10 hits, let's say the top, it would be like recall at 10. It says how many of those things that came in the top 10 were in the true top 10. So those are 2 metrics. When you start lowering the dimensionality of your vector, okay, you will lose both accuracy and recall. So, you want to be careful about that. And it's always, a per application thing. Now, let me share something. And I didn't go over this too much, but over when we're playing with our vectors and we're looking at our indexes, like I got 5 million, 1 million here. I have a very smaller index here. But if I looked at this index, we basically have one dial here, okay? Latency or recall, okay? And when I configure for latency, I might get twice the requests per second, or QPS, okay? When I configure for recall, I get more accuracy, I get better recall, okay? And then there's another way that we can increase accuracy by pumping up the partitions. And that's kind of an interesting dial. You probably end up with partitions fairly high when you're in the millions and millions of documents. But there's a certain point where if you shard your index so much, you spend more time putting the answers back together, because we get the top n answers from every shard, and then we have to put them together again. So, it's kind of a little sliding point to play with things. And I can't answer, you can take like a 1536 vector and you can make it into a 768, and you might lose 3 or 4% on your accuracy and recall, where you're not getting the true closest hit. But in some cases, that's absolutely fine. other cases, you want the best accuracy you can get. I know that doesn't answer it, but it only takes like 3 lines of NumPy to do that reduction. Now we do have another type of kind of a compression, because vectors are big. Okay, so if I was to look at these documents and I said, let's look at this one, and let's look at this vector. So I have this vector, and it's this text, and if you think about it, if you're storing 8 bytes per slot, it gets fairly big. Now, what happens a lot of times is that we end up doing quantization in the search engine side. So this is another way to take a vector and compress it by a factor of 3 and just store it as base 64 encoding. So this is coming out in 762. So I might have a vector, but then I end up encoding it. And so this vector here, it's fairly large, but it could be like 1/3 the size as a base 64 encode, and 32-bit float. So and also one of the things, I know this is a heck of a long answer, in the vector engine, the index itself, there's all sorts of things that happen under the hood. Couchbase actually, if you have less than like 10,000 documents, it does exact search. If you're over 10,000 documents, it starts to switch to an inverted index. And if you're even higher, like let's say over 20,000 or so, then we'll start doing scalar quantization and take it down to 8 bits and to like make centroids. So there's a lot of stuff where you lose accuracy depending upon how the index works. And we use 3 different algorithms in Couchbase. So if I had to scroll down and find what's going on here to like kind of explain this to you, in the vector store, we end up having an analysis pipeline, and then we segment things. And then since we use FICE has a bunch of classes or algorithms, and these algorithms, might be flat indexes. They might be inverted indexes, which are actually Vernelli diagrams. And then we get quantization where we're compressing those floats in our index itself. So, when you're talking about lowering your vectors, almost all vector indexes do something like this, where they'll trade off some accuracy to maintain their performance. And so when we get into Couchbase, we automatically tune stuff for you. So you don't have all these dials that you deal with. We do it for you, because we understand how many partitions there are, and it would start to be a little bit mind-bending. So here's what happens. When you have very, very few indexes, we basically are just doing straightforward exact search. And then we start to do an inverted index between 1,000 and 10,000. Then over 10,000, those floats are compressed to like a quantization of 8 bits.
All right. Thank you, John. Paul said, thanks, that was helpful. And he had a follow-up question. How or when might we get access to this experimental vector search tools in the CBS Web Search UI?
Oh, these guys, they're not hard to do. I wrote them in 4 hours. And since I am the product manager, I am pushing for it. We probably won't have it in June, but the next release, we will have some way in order to do what I was showing here. You come in here and you get a query helper. And the issue isn't so much putting it in. It's like, hey, how do we make it look nice? I mean, this is kind of a hacky thing I did. And this is using my own OpenAI key. So what we need to do in Couchbase, we have a product that's called Couchbase IQ that helps you write SQL and creates buckets for you and stuff. We'll probably put something where there's a rate limiter where you could do maybe 5 and 10 minutes. And then if you exceed that, then you can't do anything in an hour. And then just let people, play with OpenAI embeddings. Now, you might want to use coherent embeddings or embeddings from Hugging Face, which means that, okay, now we end up with something a little bit more unique where, say I'm in eventing, and I'll just show you this. This is eventing, that is actually to generate a vector. Okay, it makes a curl call. Okay, and it makes a curl call using a URL setting with a bearer key that I put in. Okay, so in order to do these tools right, we have to have a way to let you guys, our customers, say what service do you want to use. You get to configure the URL, you get to configure the extraction logic to get that embedding. So it becomes a little more complex than my little sneaky hack that I did. Okay.
I appreciate that. Thank you so much, John. And that means we're also almost at time. Again, if you have any questions that we're not getting to today, just feel free to ask in Discord. Paul is one of our amazing ambassadors. So, Paul, you already know how to get access to me. So, feel free to follow up if you have more questions for John. Happy to pass that along, of course. But yeah, again, thank you, John, so much for attending today. And thanks to all of our attendees today as well. I appreciate it. And within a couple of weeks or so, you should find this recording on YouTube as well.